there. All right. So what we are doing today is in this first notebook going through some overlay analysis, different ways to do so, that if you have taken GIS classes or have a background in GIS, you will know these terms. So intersection, unions, and difference analysis. We will be doing that using the travel time matrix that you might be familiar with, and then some other underlying shapefiles and geometric data. So you should all in the have a folder called data with different shapefiles and a Excel sheet. If you don't have that, then there's a guide for you to download the data, downloading a zip file, but you should have that already. So I'm going to skip that, and then if you don't have the data, go ahead and follow the instructions here. But I will jump straight into reading in our geodata. So this is familiar stuff for you. We will be reading in our packages that we need: GeoPandas, Matplotlib, and Shape these speedups. And then we have some file paths to the two first layers that we will be using. So we have a borders layer and a grid layer. So we will be reading in those with GeoPandas. So we will start by typing or giving them the names that we want. So there's one layer for Helsinki. We will read in that with gpd.read file and pass it the grid file path. And then we will do the same thing. No, pass it the border file path. And then for the grid, we will do the same, but reading in the grid file path. All right, so read that into memory. I can close that and zoom in. And then let's quickly take a look at what data we have to deal with. So let's start by plotting the first layer in a variable called AX. So we will plot the grid, as that is the underlying layer, grid.plot, and then give it a color. We can give that gray. And then if we run that, it will firstly plot the grid layer. And then on top of that, let's plot the Helsinki boundary border shape that we have in our hel variable. So hel.plot, pass it the same axis. And then since it's a border, let's give it a non-value for the color, for the fill color, and then a edge color that is blue, so we can see it. And let's plot that on top of the grid. And if we do that, then as you can see here, we have the grid in the background and the Helsinki, I guess it's the municipality border that also goes out into the sea. That's why it extends so far off from the grid. But yes, so here we have the gray grid in the background, which is the travel time matrix. So the travel time matrix is a data set with a lot of grid squares. So 13,231 grid squares. So it has the same amount of rows in the data. It covers the whole Helsinki region, and each grid square then has the travel time to each other grid square in it. So yes, and then we have our blue Helsinki municipality. And what we want to do is now do a overlay analysis and select the geometries from the grid polygon that intersects with the municipality region polygon. Okay, I hope that was understandable. So what we first need to do when doing overlay analysis and spatial analysis is checking out the CRS of our two layers. Sorry, so let's print out the CRS of our municipality polygon, which we do with hel.crs. Yes, and then we can check out whether the grid cell layer has the same EPSG 3067 CRS. So we can do that with an assertion that you might know. So assert that the hel CRS matches exactly the grid.crs. And if it doesn't, then we pass it a error message that the CRS differs between the layers. So if we run that, we can check, and if the assertion passes, if it's true, then it doesn't show us the error message, which it does. So that is good. Our two spatial layers are in the same CRS. That means we can go on to doing our overlay analysis. So there are, as we saw in the top of our notebook, there are different types of overlay analysis. So what we want to do here is we want to check what data is in the polygon, the grid polygon, and also in our municipality polygon. So that is a intersection analysis. So we want to cut out all the gray area outside of the blue municipality. Okay, so that is a intersection analysis. So let's start by then doing a GeoPandas overlay analysis with our grid data and our Helsinki borders. And we then, for the how parameter, we pass it intersection. All right, and then we want to save that to a variable that we can use later on. So let's call that intersection. Okay, so we can run this cell and it should then do the intersection analysis. And when that finished run, we can then quickly plot our data to see how it looks after the intersection analysis. So intersection plot. Let's just do it so. And indeed, we can see that it has cut out most of the grid data that we had up here, and that the border on top resembles the border of the municipality. But we now have the should have the grid cells from the data from the grid data frame. So we can check out what the contents of our intersection data frame is now. So intersection.head we can see that indeed here we have a bunch of different columns from our grid travel time matrix, and we have our polygons for each of the grid cells. Yes, so we can also to see just how much we have left inside our intersection data frame. We can, if we print out the length of our grid and then the length of our intersection, we can get an idea of how many rows from our first full data set that is left in the intersection, and therefore within the Helsinki municipality border. All right. So, yeah, just a few more things of what we see in our data intersection geodata frame. We have the different columns in our travel time matrix is either car or so. Each grid cell contains the information about the distances and the time it takes to travel to one other grid cell in the grid. So it here has one column that is called 2ID. So that is the distance from this one grid cell that we see here. No, that's not the one, but so from each grid cell to this grid cell idea, here in the from idea is which starting grid cell, and then to that other cell, both the time and the distance with either car or public transport or walking in then both rush hour and other times of in the morning, I guess. So for example, car _m_d means it's the car, and then d is for distance and m is for morning, while car rt would then be car in the rush hour and the time it takes to go from that cell to this specific cell here. All right, so we will explore the data even more in the rest of the notebook, and you will do so in the exercises this week as well. But for now, let's then save the data we have made now, the intersection from the overlay analysis. So here we have a file path already written out. It stores the data in the data folder. It's the travel times to this idea, which happens to be the railway station in downtown Helsinki. So let's save that to the file. So we will do that by intersection to file with our output file path, and then remember, as it's a GeoJSON file, to pass the driver type as well. So for that, we will driver equals GeoJSON and run that cell, and that will save the file to our data folder. Okay, I hope that was a easy to understand intersection analysis. We will be doing more of that later on, and also in the exercises. So for now, I will then continue to aggregating our data. If there are no questions at this point, but please just let me know. But yes, we will then start to aggregate the data in our intersection data frame. So what we want to do is to take a look at the time it takes to travel by car to the central railway station in Helsinki, and then show that in different plots for how long time it takes in the rush hour to get to this railway from any other point or grid cell in our intersection data frame. So to do that, we are going to aggregate the data using a function called dissolve. That takes one column of our data set and groups all the data with the same value groups it by the same value from that column. So let's start by writing the code for it. It's a dissolve operation. So let's create a variable called dissolved. And for that, we are we are taking our intersection data frame and dissolving it. So dissolve, and we pass the dissolve function by which column we want to dissolve it. So we dissolve it by, and here we can make some quotation marks and we can copy the column name here and paste it here. So we dissolve it by the car in the rush hour and then time. So let's check out how our dissolved layer would look like. If we print the head here, we can see that when we dissolve it, we get a new index to the left here of our data. We still have all the geometries and the different columns from the other that we also saw earlier, but we have a new index here that starts with -1. So -1 in the travel time matrix is NA values. So we can disregard that, but the following index numbers are the minutes it takes by a car in the rush hour to get to the grid cell. So we have 0 minutes, 7, 8, 9, and then it will continue. Having grouped, as you can see here now, there are some multi-polygons. So it has then grouped the data that we have. Okay, we can check out firstly how many cells or how many rows we have in our data. So let's turn these into F strings, and we can have in our rows, in our original intersection layer, we can print the length of the intersection. And we can do the same in our dissolve layer and run those. So from the original, we had 3,826 grid cells and rows. But after running a dissolve operation, we now have 51 different rows in our data set. Okay, so let's try to take a look at the data, the new geodata frame dissolved, to see if we can better understand what it actually contains. So we can first check out the different columns that we have. So we can see, if we run dissolve.columns, we can see all the different columns in our newly created geodata frame. And we can even see that the column that we dissolved by, the car RT, is gone from the columns list. But if we take a look at the index, we can see that the name of the index in our data frame is that column name. So that is the one we're using as our index for this dissolved geodata frame. Okay, so, and as we can see here, we have different numbers representing different minutes that it takes to get to the central railway station. So let's try to take a look at some of the data inside our geodata frame. So what we can start to do is try to select only with the index that we have, we can select specific values. So if we select, for example, 15 in the index, then that should represent all the grid cells that are 15 minutes away from the railway station. So let's try to do that. From our dissolved layer, we will use lock, and then we can pass it the index that we want, and here we want 15. So if we run that, we get we get a series, Panda series of the data from at location 15 in the index. So we can see check the data type to inspect and ensure that this is a series. So dissolve lock 15, we get a Panda series, and then yeah, we can see the data. We have already got it here. We can see only if we want to see a bit less. We want the to not clutter too much. Then we can see here we have the polygon from at the index, and we have the from idea of the first instance in the dissolve operation. So that even though there are many, it selects many grid cells, the data that is taken that are not the geometric data, then it's the first instance from the first overlay analysis. So just to be aware of that there are different cells that it will be clear also when we try to plot, or when we start plotting the data, but it does not necessarily contain all the data from all the 3,000 something grid cells that we made, but it contains the geometric data from the different time levels. Okay, so what we need to do is, if we want to plot the grid cells that are 15 minutes away from the railway station by car, we will first need to create a selection of our data, or store the data from the 15-minute selection. And what we need to do is, since this is a pandas series, it doesn't contain the or it does contain the geometry, but the geometry is not stored as a shapely geometry object that is readily able to plot. So let's take our Panda series and create a geodata frame, so we can use that to plot afterwards. So let's call this selection, as we are selecting one row of our data. And to create the geodata frame, we will do it in the old-fashioned geopandas.geodata frame. And then we can pass geodata frame a list of series. So even though we only have one series, we need to pass it inside a list. So let's take our dissolved .lock and 15 for the 15-minute mark. And then we can, as the pandas series does not contain any information about the CRS. Let's define that on the fly, so we can pass on the CRS parameter and use the dissolved.crs to do that. Yes, creating a geo data frame for that one row of data. So we can even check the selection data frame, and we can see here we have a geometry, a multi-polygon. It has the 15 index stemming from the 15 minutes. So let's try to plot that on top of our grid layer to see see which grid cells we have selected in our selection geodata frame. So similar to what we have done before, let's do a AX and then plot our dissolved grid layer, dissolved.plot, and we can give that the color, keep using gray as the background color. So here we have the initial grid cells, and then taking our selection and plotting that on top on that axis, giving that give it the red color to see it. And then what we should have now is a plot of the different cells from the original grid geodata frame, that where it takes 15 minutes to drive to the central station in rush hour. Okay. I hope that was also understandable. You will be doing more plotting in both today and in the coming exercise and next week. But I hope that the dissolving and the selection of only one based on the new index from our dissolve was somewhat clear. Then the last thing in the geometric operations notebook that we have is we can go through this quickly, but that is to simplify geometries. We can take a look at the web course web pages where that is also described. It's not something that you necessarily encounter very often, but sometimes when you do geometric operations, you might want to simplify the geometries that you have are using or have created. And so here we have loaded a shapefile of the Amazon River that you can using a shapely function called simplify. You can pass that a tolerance parameter, and it will then adjust the geometries based on that tolerance parameter that you pass it. So here in this example, we pass it a tolerance value of 20,000 meters because our CRS is metric in this instance, and then it will simplify that original geometry within those limits. So yeah, something that you might run into at different points. We could also have done it here. You could see we have our geometry for our Helsinki boundary. It is kind of rough and cut. That could also have been simplified if we had wanted to do that, but for this instance, it is okay. All right, that was geometric operations.